Greetings, YouTubers. It's Rick the Tech Enthusiast here again with the next Elegoo lesson number 5, digital inputs. In this lesson, we're going to learn a little about digital inputs using push buttons to turn on and off an LED. Specifically, we're going to use one of the buttons to turn on the LED and the other button to turn off the LED. So let's get to it. Before we begin, we'll need the following items from your Elegoo kit: the Arduino UNO R3 board, a 5mm red LED, a 220 ohm resistor, 2 push-button tactile switches, 7 male-to-male jumper wires, and the breadboard. One small confession: I purchased these handy breadboard wires. They're pre-cut to fit the breadboard's hole spacing, and I'll just substitute a few to tidy up the circuit. Regular jumpers would work just as well. First, let's talk about push buttons or push button switches. They're mechanical devices with springy little metal contacts inside them. When you press the button, they make a mechanical connection to allow electricity to flow. They come in a variety of configurations like normally open, normally closed, momentary, latching, and even multiple individual connections called poles. Ones we will use are momentary, normally open, and are commonly called tactile switches. Note these tactile switches have 4 pins, 2 sets of pins for each side of the switch. Notice how the pin sets bend in the same direction? Those are the pins that are electrically connected when you push the button or push the switch. On page 60, you'll see the schematic. And here's my version. Notice how the buttons are tied to ground. When they get pushed, they drive their Arduino pins 8 and 9 to ground or low. The LED is tied with a protective resistor to pin 5. On page 61, ignore the page 3 on the drawing, you can see the breadboard wiring diagram. And here's my version. Notice that we connect the ground pin from the Arduino to the ground bus on the motherboard. All the other devices will simply connect to the ground bus for easy wiring. Also, the tactile switches work best when spanning the center gap. So here it is all assembled. See how the tactile switches span the center breadboard gap? And we'll confirm that we are connected to pins 5, 8, 9 on the Arduino board. On page 62, the tutorial recommends that we load the Lesson 5 digital input sketch. Like before, you go into File menu, select Open, then go to the location where you extracted the Elegoo zip file. Under your language, in my case, English, go under Codes, Lesson 5 Digital Inputs, and select Digital Inputs.ino and click the Open button. The code consists of a few global variables, assigning the pins 5, 9, and 8. In the void setup, we set up the pin modes for each pin, and here we use a special parameter, input_pull-up. This parameter turns on the internal Arduino pull-up resistors for those pins. In effect, it makes them high when not externally driven by something. You see, internally, the Arduino can enable the pull-up resistors, which are connected to the +5 volt supply. While the buttons are open, the voltage potential at the pins become 5 volts or high. Some folks might also use a digital write in parentheses 8, high in the void setup, which will also turn on the internal pull-up resistors, but the parameter input_pull-up saves a line of code. The void loop consists of 2 if statements to check the button state. If you press one of the buttons, you change the state or drive it low. This operates the LED on or off. So let's upload the sketch and check it out. So here we have the circuit again. And this time, if we press the left button, the light turns on. But if we press the left button again, nothing happens. Now, if we press the right button, it turns off. If we press the right button again, nothing happens. Left button turns back on. Well, that works pretty well. So that's it. But how do we improve on this? Well, what if you only wanted to use a single button to turn off and on the LED? Many devices you see around the house only have one button to turn on or off the device. We could cleverly keep track of the current and previous states as a variable and switch the LED accordingly. However, this will probably result in misoperating, turning on or off when you didn't intend to do so. Why? Well, do you recall that I mentioned that these switches are mechanical? It's those internal springy contacts that sometimes bounce, which to the circuit looks like it's pressing the button several times before it settles to a high state. Obviously, this could cause issues making your program to work incorrectly. So how do we fix this? Normally, with discrete components, you would add a capacitor and a resistor to the circuit to slowly discharge or charge the capacitor after pressing the button. This smooths out the bouncing effect seen by the circuit. But with the Arduino, we can program a simple function to detect the bounce and simply delay accepting the change in value until things settle out. Here's a schematic I came up with. I removed one of the tactile switches and moved the other to digital pin 2. I'll go into detail on why I moved that later. The LED and resistor remain the same. Here's the breadboard wiring diagram. Other than removal of one of the tactile switches, you can see I just swung the other switch to pin 2. So looking at the code, you can see I moved the button pin to number 2. I even renamed it for simplicity. I've added several new Boolean values to keep track of the button and LED states. A Boolean is a data type that's either on or off, true or false, or low or high. And I included a counter to track the button presses just for fun. The void setup is like before with the addition of the serial begin communication function and a call to the new serial out function. The main loop checks the state of the button using the new debounce function, followed by a single if statement that checks the last button and current button states. What I'm looking for is the rising edge of the button signal, specifically when the voltage goes from low to high. If you think about it, if the last button is high and the current button is low, we found the falling edge of the button press. But once the last button is low and the current button is high, we found the rising edge. The 5 millisecond delay allows the program to skip the bounces until the signal settles down on either high or low. Now, if it meets this criteria, we increment the counter, switch the LED using a cool shorthand method of assigning the variable to its opposite value. In other words, the variable LED on is set to equal not the variable LED on's value. Being that LED on is a Boolean, it's either true or false. Then I perform a digital write to the LED pin and call the serial out function to send a message to the serial monitor. Lastly, I set the last button Boolean variable to equal the current button value, and then it loops. First, there's the debounce function that returns a Boolean value. This handy little function performs the digital read command to the button pin. If the last value is different than the current, it rechecks it about 5 milliseconds later, and hopefully it rides out the bouncing that occurs with most mechanical switches. Then it returns the current value. Now the serial out function simply sends out serial print statements to the serial monitor. This is for diagnostic purposes only. We pass on the LED on value to the local variable LED state and pass the counter value to the local variable I. The serial monitor can now tell us if the LED is on and how many times the button has been pressed. So let's upload this sketch and check it out. Here's the circuit, and the LED is off. Notice that I can press the button once and it turns on the LED. If I press it again, it turns off the LED. I can press it several times and it just works. Excellent! I recorded the serial monitor as I was demonstrating the circuit. You can see how the serial print statements display the status of the LED and the button press count. Cool! That was fun! But what if you wanted your circuit to turn on initially, run your code for checking, say, temperature, and then go into a deep sleep and automatically wake up to repeat the check? In addition, what if you wanted to be able to press a button to wake up the Arduino and then have it perform its check and then go back to sleep? Here's a schematic I came up with. Oh, that's right, I didn't change a thing. I mentioned before that I switched the button to pin number 2, and that's because the Arduino UNO only has an interrupt on 2 pins, number 2 and number 3. So by using pin number 2, we can enable the interrupt to wake up the Arduino when it's in sleep mode. Okay, looking at the code, I removed the last button and current button variables since I'll only be using the button to wake up the circuit. Big changes take place in the void setup area. Okay, we start the serial monitor with the serial begin statement like we did before, followed by the pin mode to set up the button pin, again with the input underscore pull-up parameter to enable the pull-up resistors. So far, pretty standard, but here's where it gets interesting. The manufacturer's data sheet suggests that we can save power if you set every unused pin to high or low. So we start by setting all the remaining pins to low using this simple loop. A line of code or a statement to define the LED pin doesn't need to be added because it's already taken care of in the for loop. Next, we enable the interrupt pin to use the attach interrupt command. Arduino recommends that we also use the digital pin to interrupt function. This allows us to simply pass on the button pin and let the compiler figure out what interrupt number to use. The second parameter is the function it will call after it wakes up. The third parameter is what point of the button press do you want it to trigger at. Here I chose rising for the rising edge as you release the button. Okay, now it gets a little more technical. I believe there's a guy named Kevin Darrah who does a great job of explaining how to enable the Watchdog timer, disable the analog to digital converter, and enable power down deep sleep. He does all of this without including any additional libraries. I encourage you to check out his videos. The links will be provided below. Setting the Watchdog timer is the first part of this code that involves setting a specific Arduino registers. I've included some additional comments to help the reader along in the code. If you follow along carefully, you should be able to use or include this code in your project. Okay, we start by setting the specific bits in a specific order to enable the Watchdog timer. First, we set the register to WDTCSR to equal 24. This has the effect of setting two bits, the WDCE and the WDE, to a 1 value while clearing the other bits. What happens is that the number 24 is 0001100 in binary. Note that the two 1 bits are the WDCE and the WDE locations we need to set while clearing the other bits. Next, we set the WDTCSR to equal 33. 33 is 00100001 in binary. This sets the prescalar bits and clears the WDE and WDCE bits. For the last part, we enable the WDI bit using a compound bitwise OR operator shift register trick. If you'd like more information about this trick, Kevin has an earlier video that goes over this technique. The result is that we've set the Watchdog timer for every 8 seconds, again without including a library. The Arduino datasheet has more setting options and details, and I encourage you to check it out. Okay, if you're still with me, the next line disables the analog to digital converter, or ADC. A lot of power can be saved if this is disabled. This time we set the ADEN or ADEN bit to 0 inside the analog to digital converter control status register A using a compound bit AND operator and an inverted shift register trick, where we move the register to bit 7 and then invert it. Kevin also goes over this trick in a previous video. Oh, and you can re-enable ADC if you need it when the circuit wakes up, and then disable it before it goes back to sleep. And I'll talk more about that later. Finally, we enable the deep sleep mode by modifying the sleep mode control register. I've included some detail in the code, but first we enable the power down sleep mode, and then we enable the sleep mode. So now that the setup is complete, we move on to the void loop. Here I just send a serial print line to the serial monitor, perform a digital write to turn on the LED, and another serial print to show the LED on status. Here you would place whatever code you'd want to run while it's awake. I kind of show a small delay here. We then turn off the LED, showing that that's the end of the code, and then send another monitor message and call a function go to sleep. The code jumps out of the void loop and down to a new function, void go to sleep. For diagnostic purposes, I've added a serial print here to indicate we're going to sleep. But in the spirit of saving power, we'd first disable the brownout detection circuit while sleeping. This needs to be done right before the Arduino goes to sleep. And we do this by setting the BODS and the BODSE bits at the same time. Here we use the number 3, and the number 3 is 11 in binary. And then we use the shift register trick to set them both. Next, we need to clear the BODSE and set again the BODS bits within 4 clock cycles. And Kevin came up with this clever piece of code right here. The actual line of code that makes the Arduino go to sleep is this line of code. It's an inline assembler code, and Kevin has a video on that too. You may have noticed that I have a small delay in the first serial print in this function. Well, that's because the serial print function is asynchronous, which means it'll go on to the next line of code before finishing the serial monitor output, which means it'll go to sleep before the serial print finishes. Later, when the circuit wakes, it will continue to the next line right after the sleep code, this sleep code right here. So if you want to disable and enable the analog to digital converter, you'll want to move that code before and after you disable the brownout and sleep code. Now, once it wakes, the program will return to what called it, in this case, at the end of the void loop. Here I have another serial print with the void loop ends for diagnostic purposes, which of course, all these serial prints and the serial begin statement can be commented out or removed in your final code. But it's fun for now. Okay, below the void loop, I have a function called button interrupt. If you recall, we enabled attach interrupt above, and we included this function name. When the button is pressed, it will jump to this function where I just simply increment the counter and send out a serial print. The variable qualifier volatile for the counter that we have above keeps the counter value in memory while sleeping. And then it jumps to the previous function or subroutine that the program was last at. Typically, this will be the go to sleep function, which will return back to the void loop. The serial out works like before, but there's one more function I need to talk about, and that's the ISR function. The function name must be as you see it here with the WDT_VECT as a pass parameter. Whenever the watchdog is activated, it will go here first and then jump back to whatever line of code the sketch was before the watchdog was activated. In this case, it happens every 8 seconds. Okay, I know this is very technical, but let's run the sketch and check it out. Oh, and I'll turn on the serial monitor, so while we play with the circuit, I can show you later what's displayed on the serial monitor. Okay, you can see the circuit now, and about every 8 seconds, the LED will light up and then turn off. If we press the button, it wakes up the Arduino and the LED lights up, and then it turns off and goes back to sleep. We'll do this a couple more times, and then we'll check the serial monitor. Sorry, my video skills are somewhat lacking, and I wasn't able to show you both the circuit board and the serial monitor at the same time. However, with a little video editing, I can show you what did happen. You can see for the first line, it's from setup. It starts the void loop, shows the LED is on, then it shows the LED is off. Next, it displays going to sleep. Then the watchdog wakes up the board and finishes the go to sleep function. And the sketch then returns to the void loop and displays the last line of the void loop, which is void loop ends. Then it simply repeats the void loop. Whew, that's it for this lesson. Join me next time for lesson number 6, Active Buzzer. If you like this video, don't forget to rate and subscribe. I'll try to put out a new video each week. Thanks, and see you next time.